This is a video from section 11.10. The directions say to find the Maclaurin series for f of x using the definition of a Maclaurin series. And with that, we're going to take a look at 13. Notice that f of x equals cosine x. And what I want to do from here is take successive derivatives. Notice that f prime of x is negative sine x, f double prime of x is equal to negative cosine x, f triple prime of x equals sine x, the fourth derivative of f at x is equal to cosine x, the fifth derivative of f at x is equal to negative sine x, the sixth derivative of f at x is equal to negative cosine x. So, and we can keep going, for as long as needed, okay? Now I'm going to evaluate the function and each of these derivatives at 0. So notice that f of 0 is 1, f prime of 0 is 0, f double prime of 0 is negative 1, f triple prime of 0 is 0. The fourth derivative of f at 0 is 1. And then when I take the fifth derivative of f and evaluate it at 0, I get 0. And then the sixth derivative of f evaluated at 0 is negative 1. So you notice on the even derivatives, we're oscillating between 1 and negative 1. And that includes the original function, by the way. When you look at the odd derivatives, notice that f prime of 0 is 0. And then when we take the third derivative of f and evaluate it at 0, we get 0. The fifth derivative, seventh derivative, ninth derivative. The odd derivatives, when you evaluate that derivative at 0, you get 0. But on the evens, we're switching back and forth between 1 and negative 1. So how do we compensate for that? Well, when I look at cosine x, right, it's the summation from n equals 0 to infinity. In the numerator, we get negative 1 to the n, right? Because if I replace n with 0, I get negative 1 to the 0, which is equal to 1. And that's the original up here. When I replace n with 1, right, I get negative 1, right? And it's the x squared. Because remember, it's the evens. So I'm going to take negative 1 to the n. I'm going to divide by 2n factorial. And then I'm going to take that result and then multiply by x to the 2n. And then if we write this out, right, we're going to get the following. We get 1 minus x squared over 2 factorial, right, plus x to the fourth over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. And we can follow that pattern forever and a day. And that's the Maclaurin series for cosine x. And the radius of convergence here, I claim, is infinity. And that's how we do number 13. Let's take a look at number 14. Suppose we have f of x equals e to the negative 2x. F prime of x is negative 2e to the negative 2x. F double prime of x, by the chain rule, and I'm going to do this on purpose, everybody. This is negative 2 squared e to the negative 2x. You can write 4, but if we're trying to see a pattern, I would recommend calling it negative 2 squared. And then when I take the third derivative of f evaluated at x, I'm going to get negative 2 to the third e to the negative 2x. So in other words, you want to leave things in factored form. And then when I want the nth derivative of f evaluated at x, this is going to be negative 2 raised to the n e, right, to the negative 2x. And it's pretty consistent, this pattern, because if you notice, for the first derivative, that can be written as negative 2 to the first. The second derivative is negative 2 to the second. Third derivative, negative 2 to the third. Nth derivative, negative 2 to the n. Okay, from here, I need to find f of 0. F of 0 is 1. F prime of 0 is negative 2 to the first. F double prime of 0 is negative 2 to the second. The third derivative of f evaluated at 0 is negative 2 to the third. Remember, e to the 0 is 1, okay? Dot, dot, dot. The nth derivative of f evaluated at 0 is equal to negative 2 to the n. And we can keep going from here. And we're just about done. So, therefore, e to the negative 2x is equal to the summation from n equals 0 to infinity of. Now, I'm going to get negative 2 to the n divided by n factorial. And I'm going to take that and I'm going to multiply by x to the n. So the question is, what is the radius of convergence? And we can apply the ratio test here. And it's a quick application, right? So in other words, we're going to take the limit as n goes to infinity of, and we're going to have the absolute value of negative 2 to the n plus 1 times x to the n plus 1 divided by n plus 1 factorial, right? And then I'm going to multiply by n factorial divided by negative 2 to the n, x to the n. Okay. So now, from here, we can simplify a little bit here. So we're taking the limit as n goes to infinity of. So we get negative 2 to the n times negative 2 times x to the n times x times n factorial. So I'm multiplying all the numerators, right? Now, in the denominator, right, we get, remember, it's n plus 1 times n factorial times negative 2 to the n times x to the n. Now we can cancel stuff, right? Notice here, the n factorials cancel. The x to the n's cancel. The negative 2 to the n's cancel, right? Now, what do we have left? Well, this is equal to the limit as n goes to infinity of 2 times the absolute value of x divided by n plus 1. This is equal to 0, which is less than 1 for all x. And this is going to tell me my interval of convergence and my radius. In this exercise, we're only looking for the radius of convergence. And the radius of convergence will be infinity. And so you would write r equals infinity. Just like this. Now, that was number 14. Let's take a look at number 16. Suppose f of x is equal to sine 3x. Take the first derivative. this is 3 cosine 3x. Okay? Take the second derivative. This is negative 3 squared sine 3x. And again, I do that on purpose. So we have 3 to the first, negative 3 squared. If I take the third derivative of f and evaluate it at x, I get negative 3 cubed cosine 3x. If I take the fourth derivative of f and evaluate it at x, I get 3 to the fourth sine 3x. Let's do 2 more derivatives, see if we can get a pattern. The fifth derivative of f evaluated at x is 3 to the fifth cosine 3x. And then one last one. The sixth derivative of f evaluated at x is negative 3 to the sixth sine 3x. And we can keep going. Okay? Now, let's find f of 0. F of 0 is 0. F prime of 0 is 3. Cosine of 0 is 1. F double prime of 0 is 0. So you notice, and it's not an accident, right? F of x equals sine 3x. F is an odd function, okay? And so at the even derivatives, you're getting zeros again. So when we look at f triple prime of 0, we get negative 3 cubed. And then if I look at the fourth derivative at 0, I get 0. The fifth derivative at 0, I get 3 to the fifth. And we're alternating signs. Notice how we're going from positive to negative to positive. The next one will be negative, right? So how do we account for all of this? Well, sine 3x is going to be the summation from n equals, well, we can start at 0 and go to infinity, right? Now, think odd derivatives, right? So we're starting at 3 and then going to negative 3 cubed and then 3 to the fifth. Now, how do we account for the alternating signs? Well, that's going to be negative 1 to the n times. And then I'm going to go 3 to the 2n plus 1, because remember my lower limit is 0. So I'm going to take 3 to the 2n plus 1. And then I'm going to divide that by 2n plus 1 factorial, right? And then I'm going to multiply by x to the 2n plus 1. And that's how you find the Maclaurin series for sine 3x. And that was number 16. Let's take a look at number 17. 17's good. F of x equals 2 to the x. So f prime of x is 2 to the x times natural log of 2. F double prime of x is 2 to the x times natural log of 2 raised to the second. And I hope you guys see a pattern already. When I take the third derivative of f and evaluate it at x, I get 2 to the x times natural log of 2 to the third, dot, dot, dot. And when I take the nth derivative of f and evaluate it at x, I get 2 to the x times natural log of 2 to the n. Okay. Now, f of 0 is 1. F prime of 0 is natural log of 2. F double prime of 0 is natural log of 2 squared. Don't forget that 2 to the 0, right, is 1. 2 to the 0 is 1. If I take the third derivative of f and evaluate it at 0, I get natural log of 2 to the third. Dot, dot, dot. And then if I take the nth derivative of f and evaluate it at 0, I get natural log of 2 raised to the n. Now I'm ready to set up my Maclaurin series. So 2 to the x is equal to the summation from n equals 0 to infinity of, I'm going to get natural log of 2 to the n divided by n factorial times x raised to the n. Because remember, when n is 0, natural log of 2 to the 0 is 1, and that's what I would expect to get. That's for the original function. And then when n is 1, 1 factorial is 1, and then natural log of 2 to the first is, of course, natural log of 2. So that's number 17. We're going to take a look at we'll do 19. But before we do 19, I want you to recall a couple of things. So if I take hyperbolic sine of x, this is e to the x minus e to the negative x divided by 2. Hyperbolic cosine x is e to the x plus e to the negative x, all divided by 2. Okay, that's for starters. And we can use these two identities to prove the following. If I take the derivative of hyperbolic sine of x, I get hyperbolic cosine x. And then if I take the derivative of hyperbolic cosine x, I get hyperbolic sine of x, like so. Now, with that in mind, we're going to take a look at 19. So my function is f of x equals hyperbolic sine of x. Take the derivative. We get hyperbolic cosine x. F double prime of x is hyperbolic sine of x. F triple prime of x is hyperbolic cosine x. And it's going to keep going in this pattern, right? The nice thing with the hyperbolics is we don't have to worry about the alternating of signs, okay? You'll see what I mean in a minute. Like if I wanted f of 0, now let's go back. I'm going to go back here. If I want hyperbolic sine of 0, okay, this is e to the 0 minus e to the negative 0 divided by 2. That's 1 minus 1 over 2, and that's 0. And then if I want hyperbolic cosine of 0, that's e to the 0 plus e to the negative 0 divided by 2, which is 1 plus 1 over 2, which is equal to 1, which is good to know. So f of 0 is 0, f prime of 0 is 1, f double prime of 0 is 0, f triple prime of 0 is 1, and we keep going. Okay? And so what does that tell me? So hyperbolic sine of x is the summation from n equals 0 to infinity of. Now we have to account for the odd derivatives, okay? So I'm going to get 1 divided by 2n plus 1 factorial, right? X to the 2n plus 1. Because remember, at the evens, we get 0. So there's nothing there when you're talking about the even derivatives. And that's how we do problem number 19. Suppose I ask you the following. Suppose I said, find the Taylor series for f of x centered at the given value of a. So this one kicks it up a little bit, okay? What I want to do is I want to take a look at number 25. So at 25, we have f of x equals e to the 2x. And my given value of a is 3. All right? Now, how do things look different here? Well, let's check it out. So f of x equals e to the 2x. Take the derivative. Same game. We get 2e to the 2x. Take the second derivative. We get, remember, 2 squared e to the 2x. I don't call it 4. I call it 2 squared. I do that on purpose. When I look at the third derivative of f, evaluated at x, I get 2 cubed e to the 2x. Dot, dot, dot. When I look at the nth derivative of f, evaluated at x, I get 2 to the n e to the 2x. Now, from here, I need to evaluate f of 3. Well, that's e to the 6. F prime of 3 is 2e to the 6th. F double prime of 3 is 2 squared e to the 6th. F triple prime of 3 is 2 cubed e to the 6th. And I want to keep going in that pattern. And when I look at the nth derivative of f evaluated at 3, this is 2 to the n e to the 6th. And it just keeps going from there, okay? Now, Taylor series. How does this look different? So e to the 2x is the summation from n equals 0 to infinity of. Now, the numerator, I'm going to get 2 to the n e to the 6th. All right? I'm going to divide by n factorial. But remember where my center is. My center is at 3. And so I'm going to take this and multiply by x minus 3 to the n. And a good exercise is, what is the radius of convergence? That would be a good exercise to try. And I would say that's a good stopping point for this video. This is a video on section 11.10, and we looked at problems 13, 14, 16, 17, 19, and problem number 25. Okay, thank you.